angular momentum, angular momentum, angular momentum, okay? Angular momentum. The angular momentum of a particle, the angular momentum of a particle, the angular momentum of a particle about a fixed point, about a fixed point, the angular momentum of a particle about a fixed point is defined as the moment of, is defined as the moment of, is defined as the moment of its linear momentum, its linear momentum, its linear momentum about that point, about that point, okay? About that point. It is measured by the vector product. It is measured by the vector product of linear momentum. Vector P equal to m vector v of the particle, okay? And its vector distance, angular momentum vector j equal to vector r cross vector p equal to vector r cross vector m vector v, okay? Where vector r fixed point in the inertial frame, where vector r distance from the fixed point, r distance from the fixed point in the inertial frame, okay? Inertial frame. This is point O and this is vector r and m, mass, angular velocity omega and linear momentum, vector p equal to m vector v, okay? Vector p equal to m vector v. Angular momentum. The angular momentum of a particle about a fixed point is defined as the momentum of its linear momentum about that point. It is measured by the vector product of linear momentum. It is measured by the vector product of linear momentum. Vector product of linear momentum p equal to mv of the particle and its vector distance r, distance from the fixed point in the inertial frame, Angular momentum being vector product of two vector is obviously is a vector quantity. Angular momentum is a vector quantity. Angular momentum is a vector quantity. Angular momentum is a vector quantity. Okay. Vector quantity. Its direction is perpendicular both to its direction is perpendicular. Its direction is perpendicular both to vector R and vector P. R vector B are given by the right hand screw rule. Angular momentum of a particle. Angular momentum of a particle. Angular momentum of a particle. Okay. Angular momentum of a particle. Okay. In this case of a particle of mass m decreasing a circular of a radius r. In the case of particle of mass m decreasing a circle of radius r with a uniform angular velocity of magnitude omega, and linear velocity v equal to r omega, magnitude of the angular momentum equal to mvr, so mr square omega, and its direction is perpendicular to the plane. Okay. Then the linear velocity v equal to r omega. Linear velocity v equal to r omega. The magnitude of the angular momentum. The magnitude of the angular momentum equal to mvr equal to mr square omega, because b equal to r omega. Okay. In general case also, the magnitude of the angular momentum of a particle is given by vector j equal to r mv equal to r mr omega equal to mr square omega. Okay. But mr square omega equal to d theta by dt equal to mr square integration of theta. This is the equation number first. Okay. Angular momentum of a rigid body. Next point. Angular momentum of a rigid body. Angular momentum of a rigid body. This is a rigid body. This is the axis. This is the M1 and distance is R1. This is M2 point and distance is R2. This is M3 point, this is M4 point, this is M5 point. Okay. Angular momentum of a rigid body. Okay. The sum of the momentum of the linear momentum. The sum of the moments of the linear momentum of the linear momentum of all the particles of all the particles of a rotating rigid body of a rotating rigid body of a rotating rigid body about the axis of rotation about the axis of rotation is called its angular momentum Okay, the sum of the moments of all the linear momentum of all the particles of a rotating rigid body about the axis of rotation is called its angular momentum. When a body is free to rotate about an axis, the angular velocity of all the particles When a body is free to rotate about an axis, the angular velocity of all the particles at whatever distance they may be is the same. Since the distance of the various particles from the axis of rotation is not the same, their linear velocities will be different. Okay? Consider the particle M1 M2 of the rigid body lying at distance r1 r2 from the axis of rotation xy and having magnitude of linear velocity v1 v2 respectively. In this figure, if omega is the magnitude of angular velocity, the linear velocity of the particle M1 linear velocity of the particle M1 equal to V1 equal to R1 omega. Okay? So, magnitude of linear momentum of the particle. Magnitude of linear momentum of the particle M1 equal to M1 V1. Okay, equal to M1 V1 equal to R1 omega. Hence the magnitude of momentum of linear momentum and angular momentum of the particle M1 about the axis of rotation M1 V1 R1 equal to M1 R1 square omega. Hence the magnitude of moment of linear momentum or angular momentum of the particle M1 about the axis of rotation equal to M1 V1 R1, but M1 V1 equal to R1 M1 V1 R1, then M1 R1 square omega. M1 R1 square omega, because V1 equal to R1 omega. V1 equal to R1 omega. Similarly, the momentum of linear momentum of linear momentum of the particle M2 about the axis of the particle M2 about the axis of rotation rotation equal to m2 v2 r2 equal to m2 r2 square omega. Sum of the magnitude of moments of linear momentum. So sum of the magnitude sum of the magnitude of moments of linear momentum or angular momentum of all the particles equal to m1 r1 square omega plus m2 r2 square omega plus dot. Okay, so angular momentum J equal to sigma m r square omega equal to I omega. Okay, where I equal to sigma mr square, moment of inertia of the rigid body equal to moment of inertial of the rigid body about the axis of rotation and J is the magnitude of the angular momentum. J is the magnitude of the angular momentum. Okay, velocity J vectorially vector J equal to I omega. Okay, hence the angular momentum of a rigid body is a product of its momentum of inertia and angular velocity. Unit. The unit of angular momentum is kg meter square per second or joule per second. Torque. If a force acts on a particle, if a force vector F acts on a particle at points at a point P whose position with respect to the origin O of the inertial frame is given by the displacement is given by the displacement given by the displacement vector r, the torque tau on the particle, the torque tau on the particle with respect to the origin, with respect to the origin O is defined, vector tau equal to vector r cross vector f. Okay. If a force F acts on a particle at a point P whose position with respect to the origin O of the inertial frame is given by the displacement vector r, the torque tau on the particle with respect to the origin O is defined, tau equal to vector r into f, vector r into vector f. Okay. Torque is a vector quantity, is directionally normal to the plane found by vector r and vector f, and the sense is given by the right hand rule for the cross product of two vectors. Okay. The unit of torque is Newton meter. 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 Torque is the time rate of change of angular momentum. The angular momentum vector J equal to vector r cross vector T. Differentiating this expression with respect to time, we get dj upon dt equal to d upon dt vector r cross vector T. Okay. Then vector dr upon vector dt cross vector dr upon dt vector r cross vector P plus vector r cross vector dp upon dt. But vector dr upon dt cross vector P equal to vector v cross vector m vector v equal to m cross vector v cross vector v equal to 0, and dp upon dt rate of change of linear momentum, rate of change of linear momentum equal to F, vector F, force, the force acting on the particle, acting on the particle, okay. So dj upon dt equal to vector r into cross vector f, but vector r cross vector f is the torque, torque vector tau acting on the particle, so torque equal to dj upon dt equal to tau equal to vector r cross vector f. Hence torque is also defined as The time rate of change of angular momentum. The time rate of change of angular momentum. Angular momentum. Okay. Thank you. Torque on a rigid body. Torque on a rigid body. Torque on a rigid body. Okay. Torque on a rigid body. Torque is defined as the time rate of change of angular momentum for a rigid body. Angular momentum vector J equal to R vector omega. Okay. Torque, then torque tau equal to d vector J upon dt. Time rate of change of angular momentum is known as torque. Okay. Then dj upon dt equal to I d omega upon dt equal to I into alpha vector. Okay. Where alpha vector is the angular acceleration. Angular acceleration. Okay. Torque on a rigid body is a product. So torque on a rigid body is the product of moment of inertia and angular acceleration and angular acceleration. Torque on a rigid body is the product of momentum of the inertia and angular acceleration. So torque vector tau equal to I alpha vector equal to I d omega vector upon dt. If no torque acts on a body, acts on a body, then vector tau equal to 0. But I d omega vector upon dt equal to 0 as I constant, as I cannot be 0. D omega upon dt equal to 0 or vector omega equal to is a constant. Okay. Angular velocity remains conserved. Then angular velocity remains conserved. Okay. Relation between force and torque. Relation between force and torque. Okay. Torque is defined as the time rate of change of angular momentum. Vector tau equal to d vector J upon dt. But vector J equal to vector R cross vector P. Now d vector J upon dt equal to d upon dt in bracket R cross P equal to, if we will be differentiate this value, then the value is change in d vector r upon dt cross vector p plus vector r cross vector dp upon dt okay, vector r cross vector dt upon dt. Okay, then but vector dr upon dt cross vector p equal to vector v cross vector m vector v equal to m vector v cross vector v equal to 0 okay, but vector tau equal to vector r cross vector dp upon dt equal to vector r cross vector f, because vector f equal to dp vector upon dt. Torque is vector product of position vector, so torque is the vector product. Torque is the vector product of position vector r and force vector f. Okay, good, thank you. Law of conservation of angular momentum. Law of conservation of angular momentum. Law of conservation of angular momentum. It states that when the total external torque when the total external torque acting on a system of particles is zero, the total angular momentum of the system remains constant. Constant, okay, and there is no external torque acting on a system particle, then tau equal to 0. Now torque tau equal to d vector j upon dt, where vector j is the total angular momentum of the system. Total angular momentum of the system, total angular momentum of the system, okay. Then d vector j upon dt equal to 0, r vector j equal to a constant, okay. When there is no external torque, when there is no external torque acting on a system of particles The total angular momentum, the total angular momentum of the system remains constant. Okay, thank you.